Let's recall that from geometry, we know the formula for the area of a square is A equals S squared, where A, of course, is area, and S is the length of the sides of the square. And maybe we should review that a little bit. First of all, a square is a rectangle where all sides are the same length. And suppose you have a square that's got a height of 2 and a width of 2. Then we know the area is 2 squared, which is 4. Or suppose you've got a square that's 3 by 3. So all 4 sides have length 3. The area then is 3 squared, which is 9. So I've made a table with some different side lengths and the corresponding areas of the square with that side length. And I've also made a dot plot of that data. Now in this example, the side length is the independent or explanatory variable. Area is the dependent or response variable. And there's clearly a mathematical relationship between them. In fact, we just said what it is. We said that the area is the square of the side length. So if I let y be my dependent variable and x be my independent variable, we can say y equals x squared. So since there's a mathematical relationship between the two variables, we say the variables are correlated. Now in this case, when you connect the dots, you don't get a straight line. You get a curve. It's the curve y equals x squared, but it's not a straight line. So this type of correlation is called non-linear correlation. It's still a perfectly good correlation. It just doesn't happen to be linear. Now in the examples we just looked at, the dots made a beautiful, neat curve or a perfectly straight line. They were nice and neat. But real life is not nice and neat. It tends to be kind of messy. So let's look at some more realistic dot plots that you might get out of actual data. In example 4, this is actually linear correlation. It's a little bit messy, but you could draw a straight line through the dots pretty well. So this is an example of more realistic positive linear correlation. Now, we don't know what that mathematical relationship is between x and y, but you could draw a line and then come up with the equation of the line. And in fact, in the next section, we're going to talk about how to do that. If you look at example 5, the dots, they seem to have a relationship to each other. Now, it's not linear, but I could draw some sort of curve through them and again come up with probably a formula that would describe the relationship between x and y on that curve, and therefore it would approximate the relationship between x and y on the dots. In other words, it looks like there is a relationship, a mathematical relationship between the x and y coordinates of the dots. So this is an example of more realistic nonlinear correlation. And similarly, if we look at example 6, the dots do seem to trace out some kind of curve. And we could presumably come up with a formula for that curve. So again, we've got non-linear correlation here. It's not perfect, it's messy, but there's a pretty clear relationship between the x and the y. It looks like the y depends on the x somehow. But if you look at example 7, boy, those dots are all over the place. They just look totally random. There's no line or curve that I could draw through the dot in example 7. This is what it looks like when there is no correlation between the variables. And of course, what I mean when I say there's no correlation is there is no mathematical relationship between x and y.